So chapter 14 would be the last chapter that we'll have on the exam, and we'll try to go through it as much as possible. I will try to. The last lecture would be on Wednesday of next week. I won't have anything on Friday. We'll see how far we go, and we'll stop there. So let's start with chapter 14, which is chapter 14, Polya accounting. Polya counting, and we are looking at 14.1, which is permutations and symmetry groups. 14.1, permutations and symmetry groups. Symmetry groups. Okay, so suppose I am dealing with some finite set. X is equal to finite set, which I am going to take it to be, for convenience, 1 to n, 1 2 dot 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 all the way up to n. I can look at any other set, but I'm just going to, for convenience, look at this for the sake of easier explanation. Now consider any permutation. Consider a permutation a1 a2 dot 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 an of 1 to n of x, right? Then it can be looked, can be viewed, well, it can be viewed as a function from function f from x to x, right? Where what is happening? Where f of 1 is equal to a1. No, sure, fair enough. F of 1 is equal to a1, f of 2 is equal to a2 dot dot dot, f of n is equal to an. Okay, so here's a permutation. This is not saying where 1 goes, but what is being mapped to, what number gets mapped into 1, right? So I can look at it, can write this as, can denote this as, for the sake of convenience in what is coming, we'll write it as 1 2 dot 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 n a1 a2 dot 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 an, right? And where the where a1 is the first one, a2 is the second one, that way. So even if I write random numbers, that should tell you what the value is. Okay, so for example, the permutations of 1 to 3 would be regarded as functions are 1 2 3 1 2 3 1 2 3 1 3 2 1 2 3 2 1 3 1 2 3 2 3 1 1 2 3 3 1 2, and last 1 2 3 3 2 1, right? That's 6, and these are all the permutations, right? So this is a bijection. In each case, it is a bijection. In each case, I have a bijection from 1 to bijection from 1 to n to 1 to 1. In each case, f is a bijection. F is a bijection from x to x. Right? Great. We have denoted these. Now, what I can do is, I can look at the first one, or let's say look at the second one and the third one. Okay. I can look at the second one as 1, 2, 3 gets mapped to, I'm starting from x, ending at x by f. Another copy of 1, 2, 3, 1, 2, 3. But now, how are things going? Well, one is going, let me change the color actually. One is going straight to 1. Great. Where is 2 going? 2 is going to 3, and 3 is going to 2. Okay. Similarly, I can do it for any of these other permutations. I can draw these arrows similarly, right? What I can do is then compose these permutations. Let me define something first. Definition: for all n greater than or equal to 1, for n greater than or equal to 1, let Sn be the set of all permutations, all perms of 1 to n. Okay, and we know, therefore, cardinality of Sn is equal to n factorial, right? So now, as I was saying, we can join two permutations, which is to say, I can compose two permutations. We know how to compose functions, right? You have seen composition of functions before, hopefully. Composition of permutations. Right? Given a permutation f and g, given permutations f comma g from x to x, their composition, which is denoted f composed g, FOG, is a function again from x to x, satisfying FOG of small x is exactly f of g of x. Okay, for every x in x. Okay, so what am I doing? First apply g, then apply f, then apply f. Okay, so what is going on in terms of diagrams? This is, well, g happens first, then f happens. Okay, and I am sending x to, well, g of x, and then f of g of x, and this total map is denoted f composed g. Okay, so for example, if I was looking at the permutations example, f is equal to 1, 2, 3, 1, 3, 2, and G is equal to 1, 2, 3, 3, 1, 2, right? Then how's it going to look? Well, 1, 2, 3, 1, 2, 3, 1, 2, 3. My F, I have to do G first, right? So to look at G, so this is going to be G, this is going to be F. Let me do G first. G. So what does G do? 1 goes to 3, 2 goes to 1, and 3 goes to 2, right? What does F do? Well, 1 stays at 1, 2 goes to 3, and 3 goes to 2, right? In composition, therefore, F composed G is equal to, well, 1, 2, 3. Let us look at where does what number end up. 1 goes first to 3, then it ends up at 2, so 1 goes to 2. 2 goes to first 1 and then stays at 1, so 2 goes to 1. 3 goes first to 2, then goes back to 3. So this is my permutation F composed G. Okay, so what is F composed G of, let's say, 2? Well, F composed G of 2 is G of 2, well, is equal to F of G of 2, which is equal to F of, well, G of 2 was 1, F of 1, and F of 1 was, well, 1, so it should be 1. Okay. Note, if I wanted to do in the other way, GOF is equal to, well, I can just reverse these arrows. Okay, so I can reverse these arrows. Actually, let me just do this in a nicer way. What was 1, 2, 3, 1, 2, 3, 1, 2, 3. F was 1 goes to 1, 2 goes to 3, 3 goes to 2, 1 goes to 1, 2 goes to 3, 3 goes to 2, and G was 1 goes to 3, 2 goes to 1, 3 goes to 2. 1 goes to 3, 2 goes to 1, 3 goes to 2, right? Then GOF is actually equal to, well, 1 goes to 1, then goes to 3, so 1 goes to 3, 2 goes to 3, then goes to 2, 2 goes to 2, and 3 goes to 2, which then goes to 1. 3 goes to 1, which is not the same as F composed G, right? Which was 1 went to 1, sorry, 1 went to 2, 2 went to 1, and 3 stayed at 3. Here 2 is staying at 2, 1 is going to 3, 3 is going to 1, right? Therefore in general, FOG is not equal to GOF, right? So like multiplication and division, which are commutative, sorry, not division, multiplication and addition, this is not commutative. Okay, so this gives a binary operation composition on Sn, given F comma G belongs to Sn, F composed G belongs to Sn, right? F composed G is also a permutation of 1 to n, and so it is going to stay this way. Now, in case you are wondering why f composed G is a permutation, why does no number come up twice? Why is that whenever I compose things, every number is going to come up different? Like 1, 2, 3, why can't it become 2, 2, 1 or something like that? Well, that's because if you look at the images, in terms of arrows, how are things going? If it is 2, 2, 1 in the end place, then two of the arrows from, let's say, if G composed F was 2, 2, 1, then two of the arrows of G had to be going to 2, right? That means 2 as well as 3 should have been going to 2. That is the only way that two of the numbers are going to 2, which cannot happen because G was a permutation. So F composed G is always going to be a permutation. Okay? Lemma. Even if it's not commutative, it is what is called associative. For F, G, H and Sn, F composed G composed H is equal to F composed G composed H, right? And which means composition is associative. Composition is associative. Okay, I can't leave out. I can't leave this without a proof. So here's our proof. Well, each of the functions, each of these is a function, right? Each side of, let me call this star. Each side of star is a function, right? Because it's a composition of functions. And both of these are functions from x to x. Function from x to x, right? So it is enough to show what happens to each one, each small x. Okay, so enough to show f o g o h of x is equal to f o g o h of x, right? And how do we show this? Well, let us look at the first case. What does f o g of x do? F o g o h goes from, well, the last thing that is happening is h is being sent to h of x, right, by h, which is being acted by FOG, right, which is basically FOG of h of x, right? Well, this is exactly f of g of h of x. Let us look at the other one, f of g o h. Well, take an element x. It gets sent to now by GOH. It gets sent to GOH of x, which then under f gets sent to f of GOH of x, right? But, well, this is equal to, well, maybe I should have written this separately. This is equal to g of h of x, and this under f and this under f goes exactly here, right? And so both of these sides are equal, and therefore they are equal for every function. And so we are going to write, therefore we can freely write f o g o h, right? Same way as multiplication, we don't have to be worried about is 2 multiplying 3 first or 3 multiplying 5 first, and 2 into 3 into 5. Well, you guys don't use into. 2 multiplied by 3 multiplied by 5. We don't have to worry about whether 2 multiplies 3 first or 3 multiplies 5. Okay. We also abbreviate. F o f is equal to f squared. F o dot 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 o f n times as f to the n, and in this case f to the 1, f to the 1 is just f. Okay, let me also define a nice new permutation called the identity permutation. Definition: the identity permutation I from x to x satisfies, well, it is the identity. It keeps everything the same, right? For every x. Basically, the identity permutation is given by, so I is equal to 1 2 dot 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 n. Well, 1 goes to 1, 2 goes to 2 dot 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 n. Okay, it is keeping everything in the same place. Okay, lemma. For any permutation f, for any perm f belonging to Sn, well, f from x to x, since I'm only working for one set, I o f is equal to f, f o I is equal to f. Okay, easy peasy. What is the proof? Let us look at what it does to any element x. Okay, I o f of x is equal to I of f of x. Well, I doesn't do anything, it just keeps it as it is, so this is f of x. What does f of I do? F of I of x is equal to, well, f of I of x. What does I do? Nothing. It keeps everything as it is equal to f of x, right? So in both cases, for every x in x, and therefore as these are functions, they have to be equal. Okay, therefore they are, therefore, oh, I'm not going to write that. Okay, basically, hence the lemma. Why are you stuttering so much today? Okay, great. Okay, now that I have an identity permutation, I would also like to define what is called an inverse permutation. Inverse permutation. What is the inverse permutation? Well, suppose f is equal to, let's say, I'm going to look at 1 2 3 4 5. which goes to 4, 3, 1, 5, 2. In terms of image, it looks like 1, 2, 3, 4, 5 going to 1, 2, 3, 4, 5. And how are the arrows being drawn? 1 goes to 4, 2 goes to 3. Let me do this. 1 goes to 4 with an arrow here. 2 goes to 3, right? 3 goes to 1. 4 goes to 5. And 5 goes to 2. Okay. Well, I can reverse the directions, right? And say I am looking at the function. So this is my function f. How am I going to draw f inverse? F inverse is I just reverse all the arrows. So 5 goes to 4, 4 goes to 1, 3 goes to 2, 1 goes to 3, and 2 goes to 5. Okay, so f inverse is equal to 1, 2, 3, 4, 5. Going to 5 goes to 4, 4 goes to 1, 3 goes to 2, 2 goes to 5, and 1 goes to 3. Right? This is exactly reverse of what f was doing, right? If I look back at the image, this is 1. What is the number above 1? It is 3. I am reversing that. So 1, 3, since 3 was above 1, now 1 is above 3. 5 was above 2, 2 is above 5. 4 was above 5, 5 is above 4. 1 was above 4, 4 is now above 1, right? That is how I can take the inverse permutation from the figure. Okay, call f inverse the inverse of f. Okay, and what does it do? Well, it undoes f. F inverse undoes f, right? It's moving them all back. Okay, so there are 3 ways of looking at f inverse given a permutation, given a perm f from x to x. Then f inverse is described as follows. Then f inverse is described as follows. There are 3 ways of looking at it. 1, for every x comma y in x, f of x comma y, f of x is equal to y if and only if f inverse of y is equal to x. View 2 says for every x belongs to x, f inverse of f of x is equal to x, right? Which means, i.e., f inverse composed f is actually the identity permutation. And probably you can guess the third one. For every x in x, the other one also should be true. F of f inverse of x should be equal to x, which is to say f composed f inverse is also equal to I. Inverse. Okay, and we would like to show that these all 3 are equivalent. Lemma. Given a permutation f from x to x, the following are equivalent, and f from x to x and g from x to x, the following are equal. The following are equivalent. I'm pretty sure I have used this before, so in case you aren't familiar with it, now you know. 1, g of f is equal to identity. 2, f of g is equal to identity. And 3, g is actually f inverse, or f is equal to g inverse, either one. Proof. Well, if g was in f inverse, 3 implies 1 is from view 2. From 2. 3 implies 2 is from view 3. Okay? So we are going to show 1 implies 3. Okay? And I won't show 2 implies 3 because it is exactly the same. So suppose g of f is equal to identity. Okay? So then look at g of f composed f inverse. Well, this is also equal to g composed f of f inverse, right? Which is equal to g composed g composed I, which is equal to g. But g of f I know is equal to identity. So this is identity composed f inverse, and that means this is f inverse. Therefore, f inverse is equal to g as required, right? And similarly for 2 implies 3. Okay, and so we have shown that, oh, there's a unique inverse. Okay, exercise. Given permutations, given terms f comma g from x to x, find f of g inverse. Okay, I want to find what happens when I look at the inverse of the composition. Well, solution or answer, whatever. Let us look at what f of g is. So x goes to x goes to x. F of g is, well, first I do g and then I do f, right? And f of g inverse, f of g inverse is going to reverse this process, right? So then this would become, I would again have these x's going as all these x's, but now the maps are reversed. I'll have f inverse and g inverse, right? And the direction has reversed. Well, if the directions are being reversed, this map becomes g inverse composed f inverse, right? Therefore, f of g inverse is equal to, well, what is the first thing that is happening? First, I'm doing f inverse to x, and then I'm doing g inverse. So this map is g inverse composed f inverse. Okay, check. Check. Let us compose the two. FOG composed G inverse O F inverse. Well, I know that this is just equal to FOG OG inverse O F inverse. Well, that is equal to FOI O F inverse, which is equal to FOF inverse, which is equal to I. Right? And therefore, I get this. More generally, F1 composed F2 composed F3 composed dot 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 composed FR, all of this inverse is equal to FR inverse composed FR minus 1 inverse composed dot 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 F2 inverse composed F1 inverse. Okay, so you throw the minuses on top and you reverse the direction. Okay, also this also means that in particular f to the r inverse would be equal to f inverse to the power r, right? Because what is happening? I am putting the same f1, f2, all of them are exactly equal to f, right? Define, for convenience, and define f to the 0 is equal to identity, right? The same way that we define x, any number x to the power 0 as 1, I can define f to the 0 as identity. Then by construction f to the r composed f to the s is, well, how many of them are there? F to the r plus s, right? And f to the r all the way to the s, there are r copies of, there are s copies of f to the r, so total number of copies is r times s, right? So for every integers, for every r comma s belonging to integers. Okay, no need for them to be positive. We know that these properties hold for negative numbers also, so we are going to do these as negative also. Okay. Then one final thing before for the end of this section, given a permutation, given f belongs to f from x to x, f from x to x, look at the set, look at I f squared f cubed dot dot dot, right? Well, there are only finitely many permutations, only finitely many permutations of x, therefore there exists m comma n such that f to the m is, maybe I should have just called them r and s, whatever, f to the m is equal to f to the n and m not equal to n, right? Well, then therefore f to the m minus n, let me just, because I'm using n for my number of elements, let me just stick to r and s. R comma s, r is equal to s, and this should have been So f to the r minus s then is equal to f to the 0, which is equal to identity, right? So therefore, for every f from x to x, there exists some m greater than or equal to 1 such that f to the m is equal to identity. Okay, and so note f to the m minus 1 is equal to f to the negative 1. Okay, because what is f to the m minus 1? It is identity composed f to the negative 1, so that is just f inverse. Okay, let me stop this lecture here.